Ilke Demir. Do I butcher your name too? Ilke Demir?
That's good.
It's good enough. Is an expert in computational analysis and synthesis of images. She worked at Facebook, where she applied deep learning techniques to virtual reality problems, and she has received numerous awards and honors. All yours. You want to share the screen? All yours.
Hello again, everyone. Is my screen visible? Okay, great, thank you. So that was a very nice tribute to Frank Popper, and actually a nice smooth transition with Mona's question about whether deep learning can help art or create art or predict art. So today we will talk about that a little bit, both the shallow versions and deep versions of generative art, and how we can create more tools to increase expressivity, increase decrease the time of the artists, and increase their ability to show their work, decrease their time in workflow and increase their capacity to create, actually. So thanks again for the introduction, and let's start. So I will start with this video. As you see, this is New York, flyover New York. And I want to ask, what do you think is the actual number of, actual size of information that is used to create this building, this new New York? Normally there are 4,000 buildings in Manhattan. And what do you think? Is it like, I don't know, 10 building information or 100 building information or 2,000 building information that is spent to create this new New York? Any guesses? I don't see the chat, sorry. Let me see the chat. Up to view. 1,000, 1.2 kilobytes. Okay, good assumptions, yeah. Actually, oh, I cannot go back to my screen. Okay, I can. So the information that is used to create this new New York is less than 200 buildings. So compared to 4,000 buildings, this is a much smaller representation that is used to automatically generate this city. And how automatic is it? Or how can we extract such representations from any model? So this is our topic today. So let's go back to procedural modeling. So before looking at such representations, let's have a recollection of procedural modeling and the way of generating infinite worlds. In current modeling pipelines, like Houdini as here, procedural layers are obtained by carefully designing scene graphs or context-free grammars or like shape grammars. And as an example, one procedural building like this one here on the right can be obtained by putting all the geometric, structural, material, color, and texture information and their systematic relations into a graph like this one on the left. And actually, let's simplifying a little bit more. Procedural modeling uses grammars or underlying system of rules to model geometric content like buildings, plants, clouds, cities, galaxies, whatever you can think of. And such grammars consist of, this is like an example context-free grammar. It consists of the starting symbol, which is, if you look at this parse tree, the start of the grammar, the root of the parse tree. Then there are terminals, which are leaves of the parse tree, and non-terminals, which are other rules, and which are other rule nodes, and rules, which are the derivation rules, saying that for this building, for example, the roof space goes to roof plane, and chimney. And this is this little rule here. So this is a very toy example of procedural modeling. And of course, procedural modeling has been used in many applications, like procedural modeling of cities, procedural modeling, detailed modeling of buildings, and other stylized cities or stylized urban areas like this. So going from procedural model, going from the grammar to the geometric model is well known. What we are trying to find is, can we actually, if procedural modeling is powerful, can we use procedural modeling on already existing models to overcome the lack of control, detailed grammar writing, all those like complex grammars and the dependency on the domain expertise? What if we can obtain a grammar from a geometric input like this and use the grammar for everything else? Well, inverse procedural modeling does that, but inverse procedural modeling assumes that there is a known grammar. With a known grammar, it tries to find the parameters of the grammar. So let's say the window is 2 meters. Is it 2 meters or 2.5 meters? So knowing the grammar, finding the parameters is inverse procedural modeling, which is closer to the procedural model side, right? Because we have a grammar. On the other hand, if the geometry is known and the procedural model is not known, so we are trying to extract the grammar and the parameters, that is known as proceduralization. And that's what we are exploring today as the shallow generative model. So in a nutshell, the process to obtain such representations is called proceduralization. And we start with a geometric model like this and proceduralize it to extract the grammar. Then with very simple text-based or visual edits, the artist can create many more modifications of the actual grammar. Or just by adding some subdivide and offsets, they can create an army of those buildings, and with some random heights, you can create a city from this very simple building. So this is the proceduralization network, proceduralization framework that I will explain today. The whole motivation here is to digitize from a type of digitization of the real world. Can we actually create a procedural world that can be used for completion, localization, rendering bigger worlds, or generating more content, etc. So how can we solve the content problem in a controlled way? So the input to the inverse pipeline may be images, meshes, point clouds, and almost all content that can be categorized. And the first step of the pipeline involves segmenting the input into structures that are separable from their surroundings by significant changes. So all of these images that I show around the pipeline are actual intermediate outputs of the system instead of just representative images. So for point clouds, you can, these are different segments. For meshes, these different colors represent different segments, etc. Then we label the segments. The second step either uses the labeling for as a fully automatic approach or to manual labeling, but we will mostly focus on automatic similarity detection approaches. As you can see, different repetitions are colored in the same color. Finally, so we have the segments, we know what is similar to what, but we don't know their spatial relations. So is the window inside the wall? Is the chimney on the roof, etc. So we build a hierarchy from those components, and this hierarchy actually represents the core of the patterns, core of the rules that we will express with the grammar. After, at the end of that, when we have the hierarchy, we can actually see put all of those into context of the rules and transformation matrices so that we can create rules and hierarchy of rules and export that as the procedural representation of the model. So I will flash through some works on different domains on proceduralization, and for all the papers, I put a pointer here. So if you are more interested in that domain, you can just go to the paper in the bottom and look at the proceduralization in that domain. So we worked on proceduralization of point clouds, which uses a semi-automatic segmentation approach to find the components. Then we use some consensus-based completion methods to increase the density of, increase the completion of the 3D models. Then we apply a structure-preserving direct procedural point cloud editing tool to create buildings like this, point clouds like this, from simple inputs like this. So the artist can just spend under 5 minutes to create this point cloud from this point cloud, because there is underlying procedural representation that we extract. We can also apply that to textured city models, textured meshes. And in this one, the clusters, the groups of segments are a little bit more complex, because what we want to do is to extract the rules from a city. So if a landmark is always surrounded with office buildings, we want to capture that as a city rule. Or if residentials always have a shop inside, retail inside, we want to capture that geometrically. So here you see our clusters, feature-based clustering of the buildings, and here you can see the visual components. So based on that, we proceduralize and hierarchical cluster to extract the grammar. Then the grammar can be used for creating city models, like big backgrounds for games, and all different, like keeping the same style and rules of the city, we can create infinite worlds. Another one is the proceduralization of unstructured 3D models. And here we are looking at very complex geometry like this. And the connectivity or the topology of the mesh actually doesn't matter. It can have non-manifold parts, it can have any weird geometry, but we approach it as a set cover problem over the triangle soup of the mesh. And we are trying to find the subsets of that mesh that actually repeat frequently, so that those repetitions can be a part of our procedural grammar. And after we extract that grammar, you can, the artists can use it for many procedural operations, such as splits, joins, copy paste, resize operations, and all those buildings are actually from this initial model, just by pulling, pushing, copying, pasting, and the artist doesn't need to go and fine tune, oh, like these walls are not touching together, let's glue it, etc. No, everything is procedural. You just pull a wall and the wall replicates with preserving the symmetry and the patterns of the actual model. Going a little bit further from 3D models, we can actually use it for satellite images. But here the procedural representation is a little bit different. So in this project, we realize that 75% of the world is not mapped. And we can actually extract maps, which is an hierarchical scheme, from satellite imagery. So this project, we create a generative addressing scheme like this from satellite imagery, so that it can be applied to anywhere. And finally, it can also be applied to 3D printing, because we need to have more efficient and more efficient printing and less support material in 3D printing tasks. And we can actually formulate this as a proceduralization problem, so that instead of printing it like this in much more time with much more support material, we can print it like this and assemble it like that. So this was also some proceduralization. So looking at the applications of proceduralization, here you can see the original model on the left and the edited model on the right. And most of these editing sessions are under 10 minutes. And you can still see that the style and the structure is preserved, but they are still the new models. They are still the some expressivity inside them. You can apply it to point clouds. So here, this one is the original one, and all the next ones are procedurally, automatically procedurally generated. This is an excerpt of our consensus model, that we can also use proceduralization to complete point clouds. Those repetitions can be used for having more complete and denser point clouds. We can use it for localization. So anywhere in the proceduralized place, anywhere in the rules, in the city you are, we can actually find it on a map, because when you proceduralize this street view image, we can find the same rule in the hierarchy of the city and tell you that where you are in that city. And finally, you can also create novel cities. Like here, this is from one of our SIGGRAPH papers, that you can actually create cities like this, which just like adapts to any starting symbol that you give. So what comes first? Is it the representation or the data or the generator or the generative model actually rules them all? So I asked this question because following the deep learning question, there is actually deep generative models. So the generative models that I talked about up to now are normal shallow generative models that we can understand, that the artist can like expect the outcome, etc. But going back to basics of deep learning, there are deep generative models which are trying to create novel samples based on the distribution of some data. So before we were trying to find properties of data, now we are trying to mimic samples from a distribution of data. I will go a little bit fast here, but if you are curious about the math behind each model, you can read those papers. There are autoregressive models those were the first ones that come when we are talking about GANs. But the generation is costly and it cannot be controlled. So here you can see that you see something like an elephant. It reminds you of an elephant, but maybe it has two trunks, or maybe it has an ear of a zebra, etc. There are variational autoencoders which try to maximize the variational lower bound on log likelihood of X. Here the Z is the distribution and X is the initial distribution. So this also has a good representation of the distribution. However, this is not asymptotically consistent because the target distribution is never perfect. Because it is a distribution, it's not a sample, you always have those blurry samples when you are using variational autoencoders. I mean, the maybe unconditional ones. Lastly, there are generative adversarial networks, which are the most popular ones here nowadays in GANS space. And this is a game between a generator and the discriminator. So there is that noise. And the generator is trying to transform that noise into something that matches the actual distribution. And the discriminator is trying to say that no, trying to guess whether the sample that is generated by the generator is real or fake. When they converge, when both of them are good enough, then that is the model that you try to create the fakes, because you actually match the distribution of the real data with the distribution of the fakes that are generated from that noise. So the generator knows how to transform noise into the distribution of the real samples. So these are famous GANs. With multiple generators, multiple discriminators, multiple like conditionals on the discriminator, etc. These are 3D famous GANs that can generate 3D models from images of pandas, images of elephants, etc. Or they can create complete models from part-based models, or they can create chair voxelized input from any other class distribution, or they can even do latent space arithmetic. So when I say latent space arithmetic, for example, there is this chair without the armrests, and there's this other chair with the armrests. And in the latent space, when you subtract these two, you actually get the armrests, which is actually just you are doing that not in the model space, but in the feature space, but still those features are representative of those different parts. So why am I explaining these? We are going towards my ultimate evil goal, that is there like deep grammar-like GANs? For example, can we formulate explicit rules that artists can understand? Or can we just like traverse through the latent space? So there are some very novel approaches like that with very basic shape grammars, or assembling programs for puzzle-like assembly of the parts, or some string-based representation of procedural models. But there is still the ultimate question that can we formulate and learn an explicit or implicit shape representation that mimics procedural models? And it doesn't even need to be procedural, but it needs to be interpretable and explainable, because we want the artist to not just blindly traverse the latent space, but we actually want the parametric and hierarchical nature of the procedural models. Now, gearing towards reality from those like theoretical questions, assume that we have a system that can capture infinite data. It's not infinite, of course, but capture so much data that you can actually learn to mimic the world. So this is our Intel Studios, the volumetric capture studio that can have 30 people at the same time and capturing everything in volumetric with all the properties and with all the 3D information. And assume that with the data that comes from there, we can do all of these different generative models on top of that. For example, we can retarget the humans. We can, sorry, by the way, the video is not really smooth. But we can play all of that, we can recreate all of that data. We can use it for replacing humans. We can use it for understanding what is a human, what is not a human, or put a generative art on top of that, etc. And there comes another question. So photorealism like this in 3D versus expressivity, which are not real, but the artist's influence on those 3D models, versus real simulations like this that captures the maybe weather, maybe albedo, maybe urban structure of the model. So how do we balance all of these in generative models? And what next? Like even like tying it with the proper ideas. How can we create more artist and AI collaboration tools with generative art? Or how we can create more immersive experiences utilizing AI in the loop? Or how can we create more proceduralization for domains other than architecture? Sorry, I forgot to play. Yeah. These are all captured in our studio, and this is all 3D and volumetric, and this is the underlying geometry of that. So, as I said, there are open questions, and that is the end of my presentation. Sorry if I took more time than expected. I was slow.
Okay, very good presentation. My question, of course, is how much does it cost? What kind of hardware do I need? Do I need to buy special software? Is it open source? Those are
both like awesome questions. So the proceduralization work is mostly my thesis work, and I'm planning to open source it at some point. I still haven't, but there is no blocker for it to be open source, and it can process any model, any 3D mesh, any 3D point cloud, and any satellite image. Actually, the satellite image part is online and open source. It is on Facebook Research GitHub. You can look for generative street addresses, so it is there. Satellite image one is there. 3D printing one, they're all published, but the code is not published yet. For the last part, for the infinite data part, of course, you need enough compute and enough GPUs to train your models
right.
with a high accuracy. However, after training those in a generalizable way, the trained models can be shared with everyone to do the inference on the fly. And inference doesn't need to have that much computational cost.
Okay.